All right, so today we're going to start chapter number 2 in Math 30-3. This is covering limits to measurement. There's not too much in this whole chapter. It is a pretty quick one. But the first thing that we're going to talk about is accuracy and precision today. There's a mathematical difference between accuracy and precision. We'll get into that. So here's today's plan. Like I just said, starting our second unit today. It is a pretty short unit. Today, we're going to investigate the following concepts. We're going to look at the Système International. It's just a fancy way of saying the metric system. We'll look at accuracy of measurements and precision of measurements. Those are different things, although they sound very similar. And then we'll also talk about a concept called uncertainty, which is actually very, very similar to precision. Let's get going. So first of all, the Système International, also known as the metric system, is a system of measurement that uses base units such as meters, grams, liters, etc., along with a metric prefix like kilo or centi or milli, etc. You do need to know some of the common base prefixes here. So you need to know like milli and centi and deci and deca and hecto and kilo. Let's be real here. Pretty much nobody uses this one or this one or this one. They come around every now and then, but they're pretty rare. It's the other ones that you definitely need to know a lot more of, but it doesn't hurt to know these ones as well. Now, to convert between them, it's usually easiest to first get them to the base unit. So if I said you wanted to go from millimeters to decameters, it'd probably be easiest to turn your millimeters into meters and then turn your meters into decameters. This is often done just using basically a fraction that shows an equivalent measure. Or if you have a really good intuitive sense of where to go, you can change it that way as well. I can kind of show you what I mean. So here's a bunch of examples. Complete the following conversions. I'll walk you through these ones just to show you how I do them. If you have a different method, if you have a more intuitive method in your brain that works just fine, go for it. Just do that, right? Here we go. So 40 kilometers equals blank meters. I have a pretty good intuitive sense of what a kilometer is. I know 1 kilometer is 1,000 meters, or in other words, 1 meter is 1,000th of a kilometer. Whatever floats your boat, I can tell you right now, I know 40 kilometers is probably 40,000 meters, but just knowing something is kind of silly. Some people need a little bit more structure with that, and there's nothing wrong with that at all. Here's a trick that you can use to always get it right as long as you know what your prefix actually means. We want to turn kilometers into meters, so I'm going to say 40 kilometers. I'm going to multiply this by a fraction that has meters on the top, because that's what I want, and kilometers on the bottom, because that's what I want to get rid of. Think of it this way. We're going to be keeping meters, and since we're dividing by a kilometer, that's going to get rid of this. Now, in this fraction, we want to make sure that the top and the bottom are equivalent to each other. Now, of course, meters and kilometers are different unit of measures, but we want to just write it so we have an equivalent measure for each. There's a couple different ways I could do this. I could say, okay, I know I want 1 meter, and 1 meter is the same thing as 0.001 kilometers. That was on the chart we had just back here. Notice this, 0.001 kilometers down at the bottom. That's the same thing as 1 meter. So this fraction here really is just showing you the exact same thing as what 1 meter is, right? So 1 meter and the 0.001 kilometers, those are the same thing. So if you go 40 times this fraction, 40 times 1 over this, you're actually going to find that you get 40,000 meters. Now, if this fraction doesn't work for you, let's be honest, I don't really care for it so much. Instead of doing that, if you still want to keep the fraction method, you could think of a different way where meters and kilometers could be the same thing. Well, 1,000 meters is the same thing as 1 kilometer. So now you can just multiply 40 times 1,000 over 1. You're actually going to get the exact same answer. It's going to be the exact same thing either way you do it. All right, let's try another one. This time around, we got 4,500 meters, and we want to turn that into kilometers. I'm going to use that same kind of strategy from before. So I got 4,500 meters, and I want to turn it into kilometers. So I'm going to multiply. I'm going to make sure kilometers are on the top this time. And the thing I want to get rid of, in other words, meters, is going to be on the bottom. Always, always, always put the unit that you want on the top, right? That's the thing you want to keep, and the thing that you want to get rid of, in other words, meters here, put that on the bottom. I'm going to use the same conversion factor from that last one there. I know 1 kilometer is the same thing as 1,000 meters. You could have said 0.001 kilometers is the same thing as 1 meter, whatever floats your boat. Honestly, it's going to work the same way either way. Throw that in your calculator, 4,500 times 1 divided by 1,000. This is going to give you 4.5 kilometers. It'll work every time. Now, this next one, DM, that means decimeter, I believe. Let's just double check. Yeah, decimeter. I always get decimeter and decameter mixed up. They're two different things. We're turning that into millimeters. This is going to be a bit of a tough one. I'm going to be honest with you. I would change it to meters first. So I'm going to do like a 2-for-1 deal kind of thing here, right? So I'm going to go 56 decimeters, and I want to turn that into meters. Oh, not equals, times. I want to turn that into meters, so I'll put meters on the top and I'll put decimeters on the bottom. I know 1 meter, according to that other chart, is 10 decimeters. See this? So 10 decimeters is how many are in 1 meter, right? So I'll say 1 meter is 10 decimeters. If I multiply that through, I'm going to see I have 5.6 meters. And then I want to turn that into millimeters. So we just do this again. So I got 5.6 meters multiplied by, I want millimeters. I want to get rid of meters. Well, I know 1 meter, how about, no, wait, I'll do it this way. Yeah, 1 meter is 1,000 millimeters. Yeah, that'll work just fine, actually, now that I think about it. Perfect. So 5.6 times 1,000 millimeters over 1 meter, that's going to be 5,600 millimeters. There's other ways to go about doing this. This is a tricky conversion. Let's be honest. You're not going to make that kind of conversion very often, but it is what it is. Last one here, we got 33, what is that? 33 billion millimeters equals some number of kilometers. Well, you can just do the same thing we just did before. I'm going to shorten this up just because I'm running out of room. I'm going to multiply by, I want meters on the top, turn it into meters first. I want to get rid of millimeters. Well, I know 1 meter is the same thing as 1,000 millimeters. So if I multiply this huge number here by 1 over 1,000, really just to cheat this, it's going to give me 33 million, this number right here. Then, long story short, now that we have that in meters, let's now multiply that by 1 kilometer over 1,000 meters. It's the exact same conversion, just with kilometers and meters, which is kind of neat, right? Now this is going to get rid of our meters. And what it's going to do is it's going to turn this into 33,000 kilometers. It's a weird method using a fraction. A lot of people don't like using it. A lot of people just say, you know what, forget it. I know how many millimeters are in a meter. I know whether to multiply or divide. Whatever works for you, whatever floats your boat, that's all that's important here. Anyway, moving on. So to the actual new topic today, rather than just dealing with unit conversions, accuracy and precision is the name of the game today. Now, in daily life, just in day-to-day normal conversations, the term accuracy and precision often mean pretty much the same thing. There really isn't much noticeable difference between saying your accuracy and your precision. But this is not the case in math. In math, there's a subtle difference between the two. Accuracy refers to how close a measurement is to the actual true value. When you measure something, you're kind of liable to make a little bit of a mistake. You might be off by a little bit. There's a true measurement that actually exists that maybe you didn't measure perfectly accurately to. So in this picture here that I put in here, a digital caliper, which is that device there, is used to measure a nut. It measures it to be 25.99 millimeters, which sounds like a pretty accurate measurement. But assuming the caliper is working properly, that is, like I just said, a very accurate measurement, right? However, a not so accurate measurement would be to estimate it as being about 30 millimeters. So if I was holding this right here and I looked at this and you said, oh, how big is it? I'd say, oh, I don't know, maybe 30 millimeters, which by the way is like 3 centimeters. I might have said something like that, right? That wouldn't have been very accurate, right? This, however, because we're like really, really close, like to the 100th of a millimeter, that's a very accurate measurement. Now, is it perfect? Probably not. Like, let's be real here. I'm sure these decimals could go on and on and on for a while, but it is pretty close. So I would say it is an accurate measurement. Now, sometimes we care about having high accuracy in our measurements. For instance, if you're building something with wood, you want to be as accurate as possible, right? If you're building a frame or something out of it, you don't want your measurements to be wrong. There's a certain amount you can kind of have some flexibility to, but you want to be pretty accurate. If you're off by a little bit, whatever you're building is just not going to look right, or it might not even be put together at all. Or if you're building like an actual house or something, you could be in very, very big trouble if you're off on your measurements. Now, other times, we don't actually really care much about accuracy. So it really depends on the context. In other words, on what we're dealing with as to whether or not we care about accuracy. So for example, if someone asked how far Brooks is from Medicine Hat, you probably can give that information to the nearest kilometer. Maybe if you're really not even all that picky, you could even say to the nearest 10 kilometer. So for instance, if the true distance was 103 kilometers, like it says on the sign here, maybe you just say, oh, it's about 100 kilometers. So not very accurate. Even this 103 kilometers, I doubt it's exactly that. Maybe it's like 103.25 kilometers. I don't know. But it is just a good ballpark idea. We don't care about perfect accuracy sometimes, unless we're really building something that needs to be as accurate as possible. Now, I want you to just read these real quick here. I want you to state whether or not the following are accurate measurements. If you wouldn't mind, just pause the video here and give these a read, and then I'll go over them in just a second. All right, so hopefully you kind of have some ideas in your mind as to whether or not they're accurate. So for the first one, using a ruler marked in millimeters to measure your calculator. So if you're like literally, for whatever reason, using a ruler to measure the dimensions of your calculator, and you're measuring it to like the millimeters, that probably is pretty accurate. So I'm going to say, you know what, that is accurate, assuming you know how to read a ruler. You're going to get that pretty close to what the actual measurement is of that calculator. Millimeters are a pretty small unit, so you're going to get pretty close. Next one, using your hands to measure the height of a horse. You know, that's how I think they even still do it that way. I'm not obviously not a person who knows much about horses, but I know hands are a unit of measure for measuring the height of a horse. That unfortunately is not very accurate. But here's where we kind of get in. It's kind of the same idea as this medicine hat situation. Let's be honest, oftentimes you don't really need it to be super accurate. If you have just a ballpark idea, that's fine. So I'm going to say not very accurate. If you wanted an accurate measurement as to the height of a horse, maybe you'd actually measure it in like centimeters or something like that, right? Or feet and inches if you didn't want to use metric, right? But anyway, the idea is it's not really a true measurement. It's just kind of using your hands and ballparking it, which for all intents and purposes, maybe that's all we care, right? The last one, using a meter stick repeatedly to measure the distance to the next town over. I mean, obviously that'd be a jumbo waste of time right there. I don't know why anyone would do that. Would it be accurate? Assuming you did it correctly, I guess it'd be pretty accurate. So probably, right? It would be probably pretty accurate. You're measuring it like literally to the next, like to the nearest meter. Whereas if you ask anyone else, they'd say, oh, it's 10 kilometers away. No, you're measuring it like right down to the meter. That's probably pretty accurate, assuming you didn't like mess anything up or forget how many you counted. But it's not realistic, right? And that's something that we don't really talk about too much in Math 30-3, but like, let's be real here. Sometimes it's just not realistic to get that kind of a measurement. Sometimes you don't care, right? Anyway, it is what it is. So the next thing we have to talk about is precision and uncertainty. So accuracy is how close the measurement is to the true amount. Precision, however, is a bit different. Precision is the smallest unit of measurement on a measuring device used to make a measurement. That's it. Precision is just literally like, okay, how small of a measurement did you take? So that example earlier, when you're using millimeters to measure your calculator, the precision would be to the nearest millimeter. That's the precision. Or here, another example, maybe you used centimeters on a ruler to measure your phone, right? So if there wasn't millimeters on your ruler and you were measuring it to centimeters, then your precision is to the nearest centimeter. Now here's where that comes into play. Notice how I said to the nearest centimeter? Well, with any measuring device, you're going to have a degree of uncertainty with your measurement. It's not going to be perfectly accurate. You're going to be rounding to whatever it's closest to. You're going to look at, say, oh, it's almost, I don't know, 12 centimeters or something like that. You're rounding to the nearest amount, right? Now that idea of you rounding is what we call uncertainty. Uncertainty is the margin of error in your measurement. In other words, it's just how much your measurement could be off by. Now, unless otherwise given, we are always assuming that it's equal to half the precision. So if you're measuring something to the nearest centimeter with a ruler, your uncertainty is to 0.5 centimeters. So again, if you're using 1 centimeter on a ruler and that's your precision, then your uncertainty is 0.5 centimeters. You could be going up, we would say that's plus 0.5 centimeters, or maybe you're going down 0.5 centimeters. You're somewhere in that ballpark. Now, it could be something different. If I gave you a different uncertainty, then you just use that different uncertainty. That is what it is. But just traditionally, we assume it's half of the precision, right? Anyway, moving on. So here's some examples. State the precision and the uncertainty in the following. A ruler marked in millimeters is used to measure a pencil. So if you're measuring how long this pencil is here, you just made like a dash right there, you'd say, oh, it's like 6.2 centimeters, right? Or in other words, 62 millimeters, because there's 1, 2 right there. So this would be 62 millimeters. That would be your measurement. But in terms of your precision, remember, precision is the smallest. Why did I dot the C there? What am I doing here? There we go. That's better. Precision is the smallest unit of measurement on whatever measuring device you used. The smallest unit of measurement here is to the nearest millimeter. So your precision is 1 millimeter. And then therefore your uncertainty is half of that. So your uncertainty is 0.5 millimeters. You could be a little higher, you could be a little lower. It's just an estimate. And even when I drew that line there, I didn't draw it very well. This is a little bit better. Notice the pencil, I don't know if you can see it on your screen, but it's like 1 pixel away from being at where I drew that. Maybe my line wasn't even perfectly straight to begin with. Bottom line is you could be somewhere between 61.5 millimeters and 62.5 millimeters, judging by the way that this is drawn, right? So that takes into account your uncertainty. It's your precision and your uncertainty all tied together. Anyway, moving on. Next one, a car odometer measures the distance to the nearest kilometer. What's our precision and our uncertainty? Well, in this case, our precision, remember, it's the smallest unit of measurement on our device. Well, it's to the nearest kilometer. So 1 kilometer is our precision. And then our uncertainty is just half that. You need your precision to figure out your uncertainty. So the uncertainty here is 0.5 kilometers. Next one, the temperature is measured to be -6 degrees Celsius. I'm assuming because they didn't put a decimal in there or anything like that, I'm going to assume we just measure to the nearest degree Celsius. So our precision here, so the precision of our thermometer or whatever, is 1 degree Celsius. And therefore our uncertainty, it's like beating a dead horse here, this is going to be 0.5 degrees Celsius. It's just half the precision. That's all it is, right? So your precision is just your smallest unit of measurement that you measured, whatever you're measuring to. That's it. So here's another example. Mr. Scott measures his height to be 1.82 meters using a tape measure marked in centimeters. Write his height as measured value plus or minus uncertainty. Okay, so here we go. So we know the measured value is 1.82 meters. Now I did use centimeters, so just for fun, let's turn meters into centimeters. So I'm going to say I'm going to go 1.82 meters. I want to get rid of meters here. I want to turn it into centimeters. 100 centimeters are the same thing as 1 meter, so I'm just multiplying by 100. Long story short, that's 182 centimeters. That's my height right there, right? So write his height as measured value, so 182 centimeters, plus or minus the uncertainty. Well, what's the uncertainty here? We need to figure out the precision. The precision is 1 centimeter. So precision is 1 centimeter. Remember, the uncertainty is half of that. So we'll say plus or minus 0.5 centimeters. So if I measured my height to be 182 centimeters, my actual height is somewhere between 181.5 and 182.5 because of that uncertainty. Oh, and I just said it there. What is the range, lowest to highest of possible values of his actual height? Well, just use this formula we just did here, right? You could take away your ½ centimeter. So that would give you 181.5 centimeters. That's my lowest possible height. Or if I added 0.5, I'd be at 182.5 centimeters. So that right there is my range. I'm somewhere in that range from the lowest possible height I am to the highest possible height that I am. Last thing we got to really deal with here today is adding and subtracting uncertain values. So if you have to add or subtract measurements that contain an uncertainty, the combined amount will also have an uncertainty. So if you had uncertainty in 2 things that were added together, your sum is also not sure, right? However, the uncertainty of the final amount will be the sum of the uncertainties of its parts. So if you added together 2 things that had an uncertainty of ½ centimeter each, well, ½ centimeter plus another ½ centimeter uncertainty gives you a new uncertainty of 1 full centimeter, right? So you have to add your uncertainties together as well. Let's see an example. So suppose you're repairing a line of boards on a deck. You have 2 boards you're going to use. One is measured at 3.10 meters long, and the other is measured to be 2.40 meters long. You measure this with a tape measure marked in centimeters. Write the lengths of each board using the uncertainty. Well, first of all, our precision here is centimeters. So since our precision is centimeters, our uncertainty is 0.5 centimeters. Let's turn each of these into centimeters. I think we got from that last example with my height, you just times by 100. So for that first board, it's 310 centimeters long, plus or minus the uncertainty, which is 0.5 centimeters, right? So that one board could be anywhere in that ballpark. The other board is 240 centimeters, again, going 2.40 times 100, plus or minus its uncertainty, which is 0.5 centimeters. That's all we got to do there. So those are the lengths of the boards using the uncertainty. You could have drawn this as a range. You could have said, oh, anywhere from 309.5 to 310.5, but whatever, right? I think this way works pretty darn well. Now, B, determine the total length, including uncertainty, of the 2 boards if they're placed end to end. So we're placing one board down and then we're placing the other one right after it to make one line of boards. Well, here's what we do. We're going to add these two boards together. We're going to assume they're like butted right up against each other, right? So 310 centimeters plus 240 centimeters. Well, typically you'd think that would give you, if you add those two together, you get 550 centimeters, which is awesome. But you got to realize the uncertainty in all this as well. There's uncertainty plus or minus half a centimeter on this one, and another uncertainty of plus or minus a half a centimeter on this one. So if you add those uncertainties together, we have an uncertainty now of 1 centimeter. So our final answer will be 550 centimeters plus or minus 1 centimeter because of that new combined uncertainty. Hopefully that makes some sense today, right? There's a lot of different definitions. Accuracy and precision are not the same thing. Accuracy is just how close you are to the true measurement of the object, which you need something very, very accurate and very, very like close to the actual measurement to figure out. Whereas precision is just, well, your smallest unit of measurement, right? Anyway, so for practice, I want you working on the worksheet that's there. If you have any questions, please make sure you reach out and ask for help.